There we go, we're recording now. And you don't want to know anything about trajectories for differential equations, but hopefully that'll help us stay focused. That's actually the one that I scratched and not the one that I used, it looks like, anyway. So let's see, a derivation. Let's derive something simple. I don't know, this is one of my favorites. So we start with the binomial theorem, the usual one, not the generalized one. Oh, I lost the chat screen. How did I do that? Oh, I put it in full screen, that's why. All right, start with the binomial theorem. So we'll start with x plus y to the n is equal to the sum as k goes from 1 to n of n choose k, x to the k, y to the n minus k. This surprises absolutely no one, right? And so from this, we can derive some other expressions. And in this case, by letting x and y be special values. So for instance, if we let x equal y equal 1, then we get 2 to the n is the sum as k goes from 1 to n of n choose k. So from the binomial theorem, we derived an expression for the sum just of the binomial coefficients. That's just an example. Essentially, if I call it a derivation, typically, although now that I'm thinking of it, because I just was proofreading the final before posting it, I typically think of a derivation as being an algebraic derivation. Although, to be clear, I did use the word derive on the final to mean sort of a find with explanation. I guess that might be the more general definition of a derivation. So you're figuring out what it is and kind of justifying your steps as you go along, either with some algebra or with something else. So we could derive something in graph theory. Let's say the chromatic polynomial of Kn. I mean, the chromatic polynomial of Kn. Actually, let me use the notation I'm using in the final. So I'm using subscript notation for the graphs to emphasize that it's a function of x. So we can derive this by drawing a graph here and extrapolating and pretending there are n vertices there. And so it's Kn, so they all have to be connected, right? And we're assuming, is that everybody, or did I skip one? I think that's pretty close anyway. We're assuming, oh, there, that's the one I missed, because that's K5, right? But we're assuming not 5, but n, which means there could be more, which means that if I go to my first vertex, right, there are n ways I can color that vertex. And then if I go to any other vertex, it's connected to that one, so it's n minus 1, and so on. And so that is with a slightly more explanation than that. But that's pretty much what we did in class. The idea that this should be n factorial, right? So I would consider that a derivation where it's a finding with explanation. And in a lot of things that we've done, it's been an algebraic explanation, but it wouldn't have to be. And then a proof would be, well, for either one of these, if I said something, So I derived this expression, and that, like I said, that's finding the expression with an explanation. But suppose if I were guessing at the expression, and then I wanted to verify it after the fact, then I would say, well, the chromatic polynomial of Kn is equal to n factorial. And then I would prove it. And I think last time I did something with a quick proof by induction, and I could say, well, the chromatic polynomial of K1, there's in X, I'm sorry, it's not n. What am I doing here? This should be X, that should be X minus 1, and so on all the way around. This should be X to the n falling. I knew that was wrong. There we go, X to the n falling. So the chromatic polynomial of K1, well, I've got X colors, got one vertex. That's pretty easy. That's got to be X. Then that happens to be equal to X to the 1 falling. And so I would have verified statement S1, right? And then I would say, suppose Kn or Kn minus 1, it's your choice which way you like to do your proofs by induction. I usually go Kn and then bump up to Kn plus 1. I've made exceptions for that in the past, though. Some proofs just are easier when you're dealing with the minus 1 than the plus 1. So suppose this is true for some n, and then I'm almost off the bottom of the page. Then look at the chromatic polynomial for Kn plus 1. Well, that's got to be equal to, you know, and then that's when you start to kind of play with it, and you're like, well, I have my new vertex, and then I have Kn over here in the shadows. Bring that over here into the light, right? And I'm assuming this is a graph. And so I can say, well, there are X ways to color this, and then I'm going to color Kn with X minus 1 colors. So this is equal to X times the chromatic polynomial of Kn at X minus 1. So that's X times X minus 1 to the n falling, which is X to the n plus 1 falling. And that would be a proof by induction, right? Because now we've shown that it's true for K1, and if it's true for Kn, it's true for Kn plus 1. And maybe I should have had a couple more steps here as I was going from there to there, but that's the idea. Does that work as an explanation? Although I kind of imply, since I did both examples as a proof by induction, that induction is the only way to go. And it's not, but it is a really common one for what we're doing, because we're dealing with a lot of discrete things and we're trying to show something is true for all n. Let me try to fix my light a little. Did I ever show you guys my setup? It's pretty crazy. Hang on. To show you why this is such a odd little thing, let me switch my cameras here. So I've got a webcam hung upside down off of the top of a stack of books. There's a clip in the back to hold it in place. That's a little desk lamp. And then that's where I write. So So that's my little setup that I've got here. And every once in a while the lamp gets bumped or I move it for a different purpose or something, and then I get more and more shadow. So this could be a proof by contradiction. It could be any other sort of proof. I don't want you to think a derivation is not necessarily a proof. It definitely can be. If you usually the proof of a corollary, for instance, is the kind of thing like I was doing right here. So if we had proved the binomial theorem using something like probably induction, although there are other proofs for the binomial theorem, then we could have proved this identity here in the exact same way that we derived it, because it's a special case of the binomial theorem. And so in that case, while it's not always true that derivations are short, when I'm thinking about a derivation, I'm tending to think about, a handful of algebraic steps. Sometimes they can get pretty complicated though. Does that answer the question well enough? No, I think I said I was looking for a derivation. I was not. That's the word find I was trying to explain last time. The way I was using it meant find with explanation. So some sort of a derivation or some sort of an explanation. If you don't want to, it doesn't have to be algebraic. But yeah, that was the thing, and that was part of the reason why I gave you guys the extra couple of days, is because each group had a handful of problems where they had given me an answer, often a correct one. I think there were a couple of cases where maybe it wasn't, but often a correct response, but without any explanation. And so that's what I wanted, was an explanation of some sort. And you can interpret the problems on the final in the same way. If I say derive whatever, you can think of that as find with explanation, and that should serve you pretty well. I'm going to guess that you guys, since I just posted it, haven't spent a ton of time looking at the final. I think maybe on Friday, I will just answer, we can read the final together basically, and you guys can ask me questions. You can find the typos that I missed despite proofreading it a couple of times. And I can answer questions. You can say, well, what do you mean by this? Or, how much of an explanation would you require here? Kind of set the expectations a little sooner. All right, anybody else have any questions before we get rolling? All right. Let me pull this up, minimize that. And I'm going to share my screen here. I've got, I forget exactly which page we stopped on, but it was close to this one. I did learn last time how to find the chat in the screen shared mode. So, okay. Remember this, I made this PowerPoint for the layperson who hadn't taken our course. And so with that in mind, I've repeated some definitions from earlier in the course. Here, let me just. All right, so these were completely normal definitions that we had. It's been a minute since we've talked about chromatic polynomials, but I know graph theory and graph coloring is a lot of the reason that some of you are taking the class. And so just as a reminder about the chromatic polynomial, this is my preferred notation, with the graph as a subscript instead of it all as one function where you have it as the graph and the x. It's actually not a huge deal. For me, I do prefer chi to our textbook using P for like the 8th thing. So anyway, the chromatic polynomial, recall, is the number of proper colorings of the nodes using at most X colors. And we just showed this down here, that the chromatic polynomial of Kn is X to the n falling. I mention that because it's a nice special case. Remember, the chromatic polynomial of the empty subgraph on n nodes was X to the n, the ordinary monomial. The fact that there is some overlap between the chromatic polynomials on the graphs of n nodes and the regular monomials, the like X to the n and even X to the n falling, which I know is not one that most people think of as a regular monomial. But once you've done a little bit of combinatorics, you see why it becomes pretty important. So the Stirling cycle numbers are something that we didn't spend a lot of time on. I think I mentioned them in class a time or two. I believe I gave you the explanation for them where showed you how a given permutation could be decomposed into cycles. Do you guys remember that? Let me switch over to my camera for that real quick, just to kind of. So a permutation, if we think of it the long way, I'm going to do a real easy one here. We send 1 to 3, let's send 2 to 4, 4 to 1, and sorry, I didn't mean to send 3 to 1. I meant to send, well, I guess I did. It's fine. We'll do it like this. So we kind of think of it this way, that 1's getting assigned to 3 and so on. And so this permutation can be written as 1, 3, 2, 4. The commas usually aren't necessary unless we go multiple digits. And so this is the cycle decomposition of this permutation. So this is one permutation that has 2 cycles in its decomposition, or cycle decomposition. Cycle decompositions are unique-ish, right? There's technically, I guess I'm using commas today, this is the same permutation and it looks different, but if we assume that we write cycle decompositions in, we could begin them with the smallest element in the decomposition, and we could basically, if the order of the cycle decomposition is not taken into account, there's only a single cycle decomposition for any given permutation. Another one that has 2, we could leave 1 alone and then say to send 2 to 3 and 3 to 4 and 4 back to 2. So those are some cycle decompositions. And the Stirling numbers of the first kind, they count. So here, 4, 2 is the number of 4 permutations that contain exactly 2 cycles. And I actually don't have that number off the top of my head, and it's a little bit more complicated than just enumeration that I feel like doing, but we'd get 2, 4, 3 would be another one with the 1, and then we'd get another one of those. So we get 2 of each of these for each singleton cycle. And so that's going to be 8. And then we get the 1, 3, 2, 4. We also get the 1, 2, 3, 4. And we get the 1, 4, 2, 3 cycle. Commas, not commas, just ignore those for now. I believe that means that this is, let me make sure, did I get everything here? Because that one is redundant. I believe there's only 3 of these. It's basically, let's see, it's got to be 4, choose 2, but the order doesn't matter. So that's 3. And then here, make sure there's not another one for this case. So basically 2, 3, 4, 2. So like 3, 4, 2 is the same. 2, 4, 3, 2. So 4, 3, 2 is the same. And this one is also 3, 2, 4. I think that's all of them. So I think this is 11, but I'm not positive. Did you guys follow that? There's 2 each that start with a single cycle that leaves it alone. So that'd be 8 of them, plus the 3 decompositions that involve two cycles. I can't have a 4 cycle because these have to be non-empty. So I also can't have a 0 cycle because that's an empty cycle. So I think that's 11. Is that a sufficient reminder for Stirling numbers of the first kind? All right. So an interesting little formula for these guys. And it looks, if you look at it carefully here, I can't highlight it because I'm in the presentation. At the bottom formula there, x to the n falling is equal to this sum. This is very similar to the binomial formula. If you think of it as obviously there are some differences, but you've got x to the k, you've got something else to the n minus k, you have something that behaves a little bit, a tiny bit like a binomial coefficient. That's our Stirling cycle number. And then on the left-hand side, instead of getting something like x minus 1 to the n falling, we just get x to the n falling. So it's not exact, but that is a little bit like the binomial theorem. And we get these relationships between the ordinary powers, x to the k or x to the n, depending on where it is, the x to the n falling and the x to the n rising. There are several of these formulas. Basically, any quick Google search of Stirling number identities, these are going to be near the top of the page. You know, you can Wikipedia it. It's not, they're common. The only thing that's not common, remember, is the notation for the falling factorial and the notation for the Stirling numbers. The other notation for the Stirling numbers here is a lowercase c of n comma k. That's c for cycle. There's also a lowercase s of n comma k, which is when we include the -1 to the n minus k in our with our Stirling number. And they do different things in those cases. Where did my chat go? There we are. So of course, with the negatives in there, they can't count the number of cycles. So this is one of the many, many cases in mathematics where we have 2 competing ideas and for notation. Let me give you a quick example that where probably everybody here has a preference and it's the same preference. You guys are familiar with pi, or else, you know, just hang up now, right? But who here knows what tau is? Who here's heard of tau as a, yeah, it's just 2 pi. So think about all the formulas for, you know, area of the circle, all of the things that involve pi. And remember that like pi, that's half the, all right, thanks for proving me wrong, Alex. Or I mean, Do you mean it's better than, or do you mean it's strictly greater than? Because strictly greater than is true. Oh, yeah. So pi has won, right? Pi won the culture war here. Probably tau was even, I don't even think that it was in the running earlier, but if we consider them, it would make sense in some circumstances to use tau. Um, like Chris says, circumference is tau times diameter. But then what about the area of a circle? You know, then you'd have to use tau over 2 times r squared. Well, and that seems silly. Maybe less silly because, you know, if we think if we think about um, you know, finding the area as an integral, then it makes sense to have an r squared over 2, doesn't it? So maybe tau is right. Anyway, um, that's a fun little argument that I found on the internet here not too long ago, and uh, and I'm sure you'll find adherence to tau. And but pi is the default case. Pi is the one that everybody learns about in school. So these competing conventions are everywhere in mathematics. And honestly, you know, maybe it's like the wave particle duality of uh, light. Don't fret about it. You know, just kind of embrace it all is probably the best option. So for some applications, it makes sense to think, you know, especially combinatorial applications, it makes sense to think of Stirling numbers of the first kind as the Stirling cycle numbers, the ones here that I've given. And when I think of it that way, I write it like a binomial coefficient because it has a little triangle identity like the binomial coefficient, doesn't have any negative numbers like the binomial coefficient. And in that regard, it plays really well with the Stirling uh, subset numbers or Stirling numbers of the second kind. There isn't a signed Stirling number of the second kind that I've ever heard of. Nobody talks about that. And I first learned about these um, I just got a note that my internet connection is unstable. Apologies if we get cut off. Um, I'll try to reconnect as soon as I can if that happens. I learned about both of these in a combinatorial setting where I was thinking about them in terms of the number of permutations with so many cycles or the number of ways to partition an inset. Um, and so for me, that's the one I lean toward as opposed to the signed Stirling numbers. Now on your final, I gave you the signed Stirling numbers because I think it is better for that particular context. Um, if you decide that I'm wrong as a group, not as a solo, and you decide to write it up the other way, we can all make the adjustments. The difference we're talking about is where does the -1 to the n minus k go? Is it multiplied in and inherent with the n cycle k, as I'm going to say, instead of n choose k? It just makes it easier to, instead of saying the Stirling number of the first kind with n sets and k cycles or something like, well, so how about n cycle k? Is that acceptable to you guys as a way to read that? Um, and so similarly, we can say something like, how about n block k for this one? So here, the top equation is another relationship between where the Stirling numbers kind of behave like a binomial coefficient, and this looks a little bit like a binomial theorem. Again, it's missing that +1 that you'd expect, so it's not perfect, but if it was perfect, then this would just be the binomial theorem, and that'd be weird. The second one is the equation we've had all along. This is the equation I can never remember fully. I triple checked it, typing it in here to make sure that it was right for you guys. This is the same one that we derived. Actually, we derived k factorial times this guy, right? Because that's one of our theorem 2.8 results. using generating functions and like 3 different attempts. So the notation, there's enough letters here that it's easy to get confused, but this formula gives an explicit formula for the Stirling numbers of the second kind. As near as I can tell, I have never seen an explicit formula for Stirling numbers of the first kind, either signed or unsigned. If there was one for either, then of course there would be one for the other. So anyway, that's kind of nice. That's part of the reason I think our book focuses on these. Also, partitions is something that we dealt with a little bit more than permutations. And because of this, the idea of partitioning is pretty easy to extend to graphs. So here, I think the first paper that talks about doing this came about in the 70s, but there are a handful of other more recent papers, including a couple of dissertations in the last 20 years, that have expanded on this idea quite a bit. This is a relatively new field in combinatorial graph theory. So it's the idea of a Stirling graph number. And I'm going to use the notation that matches the notation that I've been using. That is not uniform. I mean, almost nothing about notation in this field is uniform. So definitely the cap S notation is pretty common here, cap S of G comma K. I like the curly brace notation. I think it's pretty, but it gets used for a few other things too. So in those cases, it might be best to use a different notation if there's any room for ambiguity. In our class, no room for ambiguity. So this is a definitional statement. If you can partition, it's the number of ways to partition the vertices of your graph into K non-empty independent sets. So an independent set, remember, is like the complement of a clique. It is no vertex in the set is connected to any other vertex in the set. So if you have 2 vertices that are connected in G, then when you partition the vertices this way, you have to put those 2 vertices in different blocks. The easiest case is if you have an empty graph, because if you have an empty graph, then it's just the number of ways to partition n things into k blocks, which is the Stirling number of the second kind, which is why we can call these Stirling graph numbers. I found these about 3 years ago. I was looking for something else entirely, but I think I told you guys that combinatorics.org is the online journal of combinatorics, I think. Electronic Journal of Combinatorics, one of those. Anyway, combinatorics.org is completely free. So when I don't have easy access to the library's website, which I've gone through phases in my research where I didn't have access to the library's database. It's a nice place to go for results if you're not too picky about what you find, because of course it's only a single journal, but it is a big one. And I found a handful of papers on these and sort of traced them down as I had time, because it was just a cool idea. And the one thing I have not been able to find, so as far as I can tell, oops, put a pin in that. I forgot about this slide. I don't have my whole previewer up. I think it's the next slide that I want to talk about that on. So let me go back to that one. Or back to. So these 2 formulas here on, this is a bigger version of the slideshow than the one that you guys have. You guys just have this part of it. So this was slide 21 of my original slideshow. And slide 23, which should be the second to last one in yours, has these identities, which is a new formula for the Stirling graph numbers. Oh, this is the wrong slideshow. I didn't fix that. That's why I'm sorry. Hang on a second, guys. Give me just a second. I got to pull up the right PowerPoint presentation. I had an error in that one. and that I fixed when I was getting it ready for you guys. You guys have the correct version of this. Where did I put it? All right, let's share. This one. I'm not going to bother to put it in full presentation mode here. That'll make it easier for us to navigate over here on the left. All right, so the difference between this, it also means I think I can highlight, the difference between this formula and the original formula for Stirling numbers is that this one, instead of being k minus I to the n, is the chromatic polynomial of G in k minus I colors, which means that it is an nth degree polynomial in k minus I. And of course, you get G partition, or G block K, I think that's what I said, G block K over on the left. But you can check those out. Those are otherwise identical. And we get an explicit formula down below for the, sorry, not an explicit formula, that was the up above one. We get that binomial theorem looking like relationship. So G block K times x to the k falling, summed over all the k, gives you the chromatic polynomial of G in X. So the Stirling graph numbers are the coefficients of your chromatic polynomial, but not the usual coefficients. They're the coefficients if you change the basis for your polynomial space to the falling factorials. We had, like most people have had linear, right? If you haven't had linear and I say change the basis, then that might not make sense, but they're the coefficients of the falling factorials as opposed to the coefficients of the regular monomials. So we can pull the pin now, not of the grenade, but out of the thought. And the thing that I have not been able to find is Stirling cycle graph numbers. So we've got Stirling partition graph numbers, or Stirling graph partition numbers. Not sure where to put the modifier there. But I have not found them anywhere, and I've played around with a number of definitions. This is the current definition that I'm playing around with. So since we know that this statement is true, that the chromatic polynomial of Kn is x to the n falling, and x to the n falling, this is another one of those many, maybe it's the one I gave you earlier. I think it's the one I gave you earlier, of binomial formula-like identities for the Stirling cycle numbers. Then can we extend that so that it's true for any graph G? Then we could define G cycle K as G cycle K as the coefficient of x to the k. In this case, I pulled out the -1 to the n minus k. Maybe you want to include it. Remember that the yeah, sorry about that. My youngest two have just decided that they hate each other. It'll be better in a few minutes, but class will be over by then. So the coefficients, remember, of your chromatic polynomial, when you look at them, when you write it out, they have to be have consecutive powers, right? And they have to have alternating signs, and when k is 0, you would get a constant term normally. Remember, we don't get a constant term in our chromatic polynomials, but that's okay because Stirling cycle numbers, think about what cycles mean. You cannot have a cycle decomposition with 0 cycles. The minimum is 1, so that's defined to be 0 usually. So this is my current working definition. I told you guys that I am incredibly bad at closing anything. So this is one of my current research projects, and I don't mind sharing it with students, because if a student were to do something more with it than I have, then, you know, I'd be happy to work with them. And because the chances, I mean, you know, class will be over by then. That's kind of my idea. So I've asked you to work with this expression or a similar expression on the final, with some of the things I know to be true. And if you get interested in it, then absolutely, you know, we can talk about it. So that's really all I wanted to tell you guys about Stirling graph numbers, unless you had any questions. All right, let me show you real quick. I'm thinking that I'm not going to do this semester. I'm not 100% sure how next week is going to go. So Hamiltonian cycles or Hamiltonian chains, paths, and then eventually cycles are where I would normally go next in this semester, but I don't normally assign a group project for a final, and it's not necessarily a short one. So I'm thinking here that Friday I will answer questions about the final, and we can have a little read along or whatever. And the next week I will just be available to answer questions kind of by appointment. And I just wanted to tell you what you were missing out on. The one topic that I have covered more times than not, it's in my optional material, but I almost always get to it. But we're going a little more in depth this semester into some of the things that I normally skate over. So I feel like it's okay to skip this, but if this was something that you were interested in and you didn't get to it and that bummed you out, you could let me know, and I would be happy to talk to you about it, you know, independently, as opposed to make it a, you know, something that the whole class had to do. So before this in chapter 11 is the relatively simple Eulerian paths and chains. So that's the whole starts with the bridges of Königsberg problem. Though that's really settled stuff. A lot of you guys learned about it in grade school, maybe not the exact like general formula, but it's pretty easy to extrapolate. So I would encourage you guys to kind of skim chapter 11 at some point, if this is the sort of thing that you might need in your field. Otherwise, if you're teaching, then I would encourage you to read the early part of chapter 11 so that you understand more about it than what it says in the textbook that you might use later, in case you get a student that challenges it or something. Does that seem amenable to everyone in terms of a plan for next week?